How are you?
I'm good. How are you?
Fine, thank you.
Where are your headphones? Huh? I don't have a microphone. You don't have? I wonder if I put my headphones in the microphone from the computer store. Yeah.
What's going on?
Can you guys still hear me?
Yeah.
Yeah.
Okay. Maddie's asleep, so I'm trying not to be loud.
Right on.
What's that? Okay. Well, why don't we get started? What's that noise?
I think it's outside.
Did you guys do the prep? Like,
I did the first part. I didn't do the second part.
I did both sections.
Awesome.
Yeah, I did both sections too.
The second section's fast.
Yeah.
Cool. All right. Well, let me open it up and then we'll get going.
I'll do the first one.
Okay.
One is this: what's a sampling distribution? The sampling distribution is like all the possible values that that x could be. So like the mean could be. So if you have like a really large group, like 5,000, you take say 25 out of that, and then you take the mean of whatever that is, and that's your like sampling distribution. So there could be a ton of different groups.
Right.
Yeah.
Yeah, I think the way I understood it was like when you have a bunch of different samples, the means of all those different samples.
Mm-hmm. So it's what all the values could be.
Yeah.
Okay.
So one mean could be different than the other.
Right. Because like, although they'll be close, they'll form like a normal distribution.
Yeah.
I guess that's the second question.
Mm-hmm.
Okay. What is the shape of the sampling distribution of the sample mean when the data are normally distributed? It's normal bell-shaped.
Yeah.
Yeah.
Okay. Danielle, you want to do 3?
Yeah. What is the shape of the distribution of sample means when the data are not normally distributed, but the sample size is large? It's like this, right?
Yeah,
Yeah.
it's normal.
So that just means normal.
Yeah.
Awesome.
Okay, what are we on, 4?
Mm-hmm.
Okay, 4. How does the shape of the distribution of sample means change when the sample size is increased? It doesn't really change. It becomes, I guess, more narrow most of the time, or more normal.
Yeah. Like the key says more normal.
Mm-hmm.
And then, let's see, 5 said, what is the difference between the central limit theorem and the law of large numbers? I didn't really get like what it didn't seem like it was that I don't know, it kind of seemed like common sense.
Mm-hmm.
It's like I know there's a theorem for it, but it's like, well, duh. So it says that the central limit theorem is that if the sample size is large, the sample mean will be approximately normally distributed. So
Yes.
it's exactly what you said in the one before that.
So it has to be large enough for it to be normal.
Mm-hmm.
I mean, if you have like 15,000 numbers and you only use like 7 for your sample, it could be way different.
Okay. So, and the number they said that you have to have an accurate sample is 30, right?
Mm-hmm.
That's like the minimum number.
Yeah.
Okay, and then the law of large numbers was just that as the sample size increases, the standard deviation of the sample mean decreases.
Yeah.
So the distance between the numbers gets smaller as you get more and more numbers.
Yeah, the standard deviation gets smaller.
Mm-hmm.
I have a question. I was reading, and I think central limit theorem we can use when we use like a normal distribution, and the law of large numbers we use when it's not normal, right? Or both are using?
Let me go look at the book again. I'm not sure. I don't want to say yes or no.
I think the central limit theorem says that if the sample distribution is large enough, then it will be normal. But I don't know if it's only limited to being used in like one case or the other. Because the central limit theorem has the formula that's the standard distribution over the square root of n. And that gives you the standard distribution of the sample mean. So I don't know if you can only use that when it's really large.
I was confused because in the book, in the last part says, if the parent population is normal, the distribution of the sample means will be normal for every sample size. And then said, even if the parent population is not normal, the central limit theorem guarantees that the distribution of the sample mean will be approximately normal if the sample size is large enough. Thus I was thinking if I need to use one when it's normal and central limit theorem when it's not normal.
I don't know if this is something that you use or just a concept to understand.
Oh.
Because I think like with the central limit theorem, it's just saying that like even if all your numbers are way different, when you pull samples and you take the means and you do it enough times, they're going to be fairly consistent with each other.
Right. Like although you'll have some that are like super far to the bottom or the top, the means of all the different samples will end up being relatively normal.
So even if your parent sample or your parent group is way random and scattered, when you filter it down and do your samples and take your means, they're all going to be pretty close.
Yeah, I think so. Did you guys open up that little app thing on the reading?
The sampling distributions.
I feel like that kind of gave a good example. Yeah. So like
just play with the custom one.
Right. So let me mirror my screen because I want to see if I'm understanding it right. Okay. So with this one, the parent population up here is really, really skewed this way. Right? But when you take the mean of all of these and bring it and distribute those, it brings it back to more normal.
Like look at the shape is normal.
See how this is way skewed this way? The central limit theorem says that when you get a ton of these, like 100,000 of these, it's going to make this more and more and more normal.
And the normal just means that it's the bell shaped.
Right.
That you have a normal distribution.
Right.
Those.
Okay. Yeah.
Right. Because like on this side is not bell shaped.
So do it now with a custom one.
Okay.
Yeah.
I mean, just like I did a tower on the left, kind of spots in the middle, and then a tower on the right.
I don't know how to do that.
Oh, you just click around and drag the mouse.
Oh.
That looks good. And then do a bunch on the right side and some in the middle too.
Okay.
And then if you do the animation, then you can watch the way it stacks up. And then
Right.
after a while, just click on 100,000 and see what it does.
Yeah, so I'll do animate.
Mm-hmm.
So see how that's relatively bell-shaped?
Mm-hmm.
Even though these are not even close to bell-shaped.
Oh, yeah.
With enough samples,
Right.
it will become normal.
Right, like with over here, you can see I did like 800,000 samples. So 800,000, or the means of 800,000 samples right here. And that's what makes it, so that's just what the central limit theorem, I think, means.
Uh-huh.
Okay. Thank you.
And then the law of large numbers is just that as the sample X gets closer to the mean, or the sample mean gets closer to the mean of the whole thing as the sample gets larger.
Right.
So like if you do the 5, it might not be super close
Right.
to the mean, but then do the 100,000 and it's right on the mean.
Right. Okay.
And then
Please.
6.
6. When is X normally the mean of X normally distributed?
When
I'm
the
not
sample size is large enough.
Uh-huh.
right. So that's just what you were saying.
Mm-hmm.
When the sample is large enough, then the X is, or the mean of all your numbers is going to be normally distributed.
That's when the law of large numbers comes into play.
Right. Okay.
And then part 2. Part 2, you had to make this little thing of paper and do 30 of them.
Uh-huh.
And then pull 5 random ones out. And you said you did this, Daniela? Did you do this one?
Yeah.
What did you get? For my mean, I got 44,300.
For my mean, I don't remember what I write. I don't remember where I write mine. Give me a minute.
Okay.
I have like 3 notebooks here today. I don't know why. Oh my gosh.
You're okay.
Okay.
Mine was just a little bit below the mean when I did my 5 numbers.
Yeah. I need to find my. Okay, probably I went here. Okay, my sample mean.
Mm-hmm.
Good. Oh my. Really, I don't know where I write. But no, I can find.
That's okay.
Give me a minute. I can. Oh my gosh. Okay, I can find it.
It's fine. We can just use my number. So then B says on the graph, you're supposed to mark. Well, I think that's pretty crazy that there's 142,506 possible combinations of salaries.
Yeah.
If you pick 5 out of the 30, but that makes sense. And then you look at the distribution, and that is what it is.
Mm-hmm.
If you were to graph all those, that's how it would end up. So mine is just below the mean, coming in at 44,300. It's still pretty high up on the bell curve if you look at it. And then does your sample mean appear to be unusual? And it doesn't, because it falls in the meat of the graph.
Right. Is it within the first standard deviation? Do you think?
It doesn't give you a standard deviation. At least I don't think it did.
Based on the graph, you might say that
yeah, it would totally fall within the first one.
Right, because it's like 40. Looks like it's 4,800 and 4,400 is kind of what they're getting at.
Mm-hmm.
Okay.
And D, compare your mean.
Well, let's do this real fast. I was just looking at the assignment, and there's a random.org generator.
Uh-huh.
And so you don't need to cut out those papers. You could just ask it to give you 5 numbers within 1 and 30. So my numbers are 9, 26, 11, 1, and 14.
Okay.
So what do those correspond to? So what is on them?
9.
So 9.
42,800.
Okay, one second. Let me scroll down.
Here,
Okay.
how about you read them off to me, and then I'll just write them down.
Okay. So 42,800 is what you said for 9, and then for
Yeah.
26, 49,800.
Mm-hmm.
And then for 11, 45,300.
Mm-hmm.
And for 1 is 45,000.
Mm-hmm.
And then 14 is 48,500. So I have my calculator if you want to read those back.
Yeah. So it's 42,800,
Mm-hmm.
49,800, 45,300, 45,000, and 48,500.
What was the third one?
45,300.
Okay. Divided by 5. That can't be right. Do it again.
42,800.
Okay. Plus.
49,800.
Mm-hmm.
45,300.
Mm-hmm.
45,000. 48,500.
Mhm.
Yeah, 46,280. 46,280. Which is right smack dab in the middle.
Yeah, yours falls right in the middle.
Okay. So now we're answering questions about that now.
It's just the last one is compare the answers that you got from 7 and like what do you see?
Mm-hmm. Well, from the numbers that I just got and the numbers that you got, they're within 1 or 2 standard deviations,
Mm-hmm.
which means that they're usual.
Yeah. And they're close enough for it to not be very weird.
Right. Yeah, like the definition for unusual or not unusual is within -2 and 2 of the mean. So, okay. The graduate management admission test is used as an admission criterion in many Masters of Business Administration programs. I'm sorry, Daniela, that they have questions like that. That's crazy.
Yeah.
That'd be so hard to read.
If I had to do it in Hungarian, it would just kick my butt.
Yeah, I wouldn't do it. Okay, the scores on the GMAT are normally distributed with a mean of 529 and a standard deviation of 113. Consider a simple random sample, or n equals 10 students taking the GMAT.
So A is what's the shape of the distribution of the sample means for all such samples. Well, it's normally distributed,
Normal. Uh-huh.
so they're all normal.
So bell-shaped. Mm-hmm.
Bell-shaped. B,
Right.
how do you know that the distribution of the sample mean has this shape?
Because the parent has normal distribution.
Yeah.
Even though n isn't that big, because the parent has normal distribution, then you're good.
It should fall within that fine.
Right.
What is the mean of the sampling distribution of sample mean scores for all such samples?
529, right?
Yep, the mean's 529. And then what is the standard deviation of the distribution of sample mean scores for all such samples?
35.73?
Yeah, 0.734,
Ah, 34.
Is that 529 divided by what?
No, you take the standard deviation. This
Oh,
is
113 divided by the square root of 10.
Yeah.
That's right.
How do you say in English, like, when it's not the square, when it's
squared.
the opposite to square? What is?
Yeah,
Square
so
root.
like that?
Square? No. The other one is like, I don't know how do you write in the computer. It's the opposite to this in math.
The opposite of what I wrote.
Like, Oh, I'm going to write here. It's better. Okay. This one. No se ve. Okay.
Square
Oh.
root?
Yeah, square root.
Okay.
Yep.
And then if it's like the third square root or the third root, it's just the third root, like x, the 1/3.
Dude, it's cube root.
Or the third root or the fourth root. So the only ones that are weird.
Where's it at?
You gotta talk, Andrew.
There it is. Cube root.
Right.
Yeah, so that's the cubed root.
It's the standard deviation divided by the cube root of the number, right?
The number
It's
n.
The square root. Okay, let's open that test or the quiz.
It's 12 long.
Oh darn it!
That's not that long.
It's not that long. Oh, the other one was longer, wasn't it?
Okay, round to 3 decimal places.
The parent is right skewed.
What was that? Oh, had an airplane flyby?
Okay. So when you're taking this, so n isn't, or 5 isn't big enough to get it back to normal.
No, but so I just did it on the. So it's skewed left, but look at what it came up with.
1 second.
So I don't know how you mark that.
Wait, show me again.
Can you see it? If I talk right now.
Oh yeah.
Hey, let me just flip my camera. That was dumb. I mean, that's 5.
Yeah, that's dumb.
So I don't know. I mean, luckily we get 2 chances. I would say it's
Right. It's still right skewed.
because there's only 3. It's not normal. I would say skewed right.
Right. Okay, while you're taking the sample size of n equals 100, what is the shape of the distribution means it's going to be normal.
Yeah.
Because n is over 30. Okay.
When you are taking a sample size of n equals 100, what is the shape of the distribution of means histogram when the parent population is right? How do you pronounce skewed? Skewed. Entonces, so I think.
Oh, entonces.
is skewed, right? Right?
Nope.
I think it's normal.
What is 100?
Yeah, because n is 100, so you have that many samples.
Oh, yeah.
So remember with the large numbers that we talked about and the law that
it is normal.
No matter what the top is, with enough samples, it's going to look normal.
Okay. So question 5, why don't you read that, Daniela, so that we all stay on pace?
Yeah?
Yeah.
When you are taking a sample size of n equals 5, what is the shape of the distribution of means histogram when the parent population is normally distributed?
It's normal.
Mm-hmm.
It's going to follow its parent.
Yeah.
Mhm.
6 is the same.
Uh-huh. So although it's not going to follow its parent because the n is big, it's going to be normal because the n is big.
Mm-hmm.
Okay. When would the distribution of means be normally distributed? Choose all correct responses. So when the data are drawn from a population that is normally distributed and the sample size is small,
Yes.
yes. When the data are drawn from a population that is normally distributed and the sample size is large, yes.
Right? Yes.
Mm-hmm.
Data are drawn from a population that is right skewed and the sample size is small, no.
No.
Data are drawn from a population that is right skewed and the sample size is large, yes.
Right?
So the first, second, and last one.
Mm-hmm.
Okay, Daniela?
Which of the following gives the best explanation of the central limit theorem? If the parent population from which the data are drawn is normally distributed, then the sample mean will follow a normal distribution, right? And the other,
That's true, but let's read the other ones too.
okay, for bell-shaped data, approximately 6/8 of the data will be within one standard deviation of the mean. I think it's not that one.
Right. You don't need to keep reading.
If the sample size is large, the sample mean will be close to the population mean. If the sample size is large, the shape of the distribution of sample means will be approximately normal. So could we use one?
I think it's the last one.
Yeah, I think it's the last one too. Although the first one's true, I think the central limit theorem is the last one.
Mm-hmm. The shape of the distribution of sample means will be, yeah.
And the one right before that describes the law of large numbers.
Mm-hmm. Right.
Okay.
Okay. So let x be a random variable with population mean u equals 10 and population standard deviation hockey puck equals 6. Suppose a sample of size n equals 36 is drawn from this population. What is the mean of distribution of the sample size?
10.
Yeah, isn't it the same?
Yeah.
It should be.
Okay. And then what is the standard deviation? It's going to be...
Hold on, wait, isn't it? Okay, well, the standard deviation would be 6 over the square root of 36. So it's just
Right. Right. Yeah, 'cause I don't think you would do anything to the mean.
Oh yeah, it's
To the
one.
mean? Yeah. Okay. And then, so 11, regardless of the distribution of the population, if the sample size is large and is greater than 30, what would be the shape or distribution of the sample mean?
normal.
Normal.
Normal. Uh-huh.
The theorem that would justify the last question.
When the theorem will justify your response to the last question.
Is this a trick question because they put the word theorem in the question? I think it's the law of large numbers.
Yeah, it's the law of large numbers.
Okay, I'll submit.
So the central limit theorem is if the sample is large enough, the sample distribution of the sample mean will be normal.
Shoot. So.
And then the law of large numbers is that the closer to the standard The law of numbers means closer to the standard deviation, closer is more accurate to the mean. The sample X gets closer to the mean the larger the sample size. So I'm pretty sure it's law of large numbers.
Yeah.
Actually,
I'm not saying that because n is greater than 3, so it's saying like as your sample.
gets larger, it will get more normal.
I'm gonna do the central limit theorem, and I'll submit mine. And we'll see.
Okay.
But it's law of numbers, right?
Based on what he just said, I'm not sure.
So my guess is
Because-
the law of large numbers. That's the one I'm betting on. That
No.
as it gets,
I got 100%, and I did central limit theorem. So everything we have except for that one was right, and so the correct answer is the central limit theorem, because it's talking about the number of samples.
Samples.
The law of large, and read what you said about the law of large numbers again, Andrew.
what
The law
what
of
I said
large.
is
Okay.
the sample mean gets closer to the mean as the larger the sample.
Right. So if you go back up to, where was it? If you go back up to this, to question 9, what is the mean of distribution of sample means? We're saying that it's because it's over 36. Oh, because n is over 36, it's a sufficiently large number.
Yes.
That the mean of the entire thing is going to be close to the parent mean.
Yes.
And so that's the law of large numbers. It says
Okay.
as your samples increase, all of your means are going to be the same as your parent mean.
Why did we need the applet open?
I don't know. I didn't see
We
any.
didn't need it for anything.
No, and we got them all right. So
Cool.
So, okay, entonces the central limit theorem says that the sample distribution of the sample mean will be approximately normal if the sample size is sufficient large.
Right.
Sufficiently large is 30 or more.
right.
Yeah.
So when you see central limit theorem, you need to think normal. When you hear law of large numbers, you need to think about the actual number of the mean. So the central limit theorem talks about the shape of the entire histogram.
Yeah, I got it.
Yeah, okay.
Yeah, thank you.
Eric, she knows.
I know. Entonces, we're going to meet on Thursday?
Entonces, yes.
Okay. I'll post this right now.
Okay. Gracias. Thank you.
Adios, amigos.
Adios.
Bye.